today. I think we're super excited to have you here. I'll let you run.
Thank you very much for having me, and thank you everyone for making time today to joining and finding time in between wrapping up your work before moving to Christmas holidays and searching for Christmas presents. So my name is Alexandra Posoldova. I'm Senior Data Scientist at Blackbook.ai, which is RPA and AI consultancy company. And today I would like to talk to you about various phases of machine learning operations. So what is machine learning operations, or MLOps? It is like DevOps for machine learning. And that's all you need to know about MLOps. So any questions? Just kidding. So we'll start with machine learning development lifecycle, and we'll walk you through all of the stages and explain what maintenance is involved and operations is involved in each of the stages. So let's start with data source. So that's a place where your data comes from. It can be database, CSV file, media file, Excel, JSON, anything. So you need to manage your data source, manage the space. If you manage the hardware, making sure there is enough space as your data is growing, making sure the data is consistent. So if it has certain structure, it needs to follow that structure. Making regular updates to your data. It's helpful if you maintain different versions of data. So if you want to reproduce some machine learning results, you know what data was used for inference or training. Then as you ingest the data by your machine learning pipeline, you need to manage that pipeline, whether it's ingested as a batch or as a stream. How often is it updated? Is it daily, weekly, or if it's streamed, then it's continuously updated? And monitoring for data drift. It often happens that the data that the machine learning model was trained on changes over time, statistically becomes different. And great example is this year when COVID hit us. And so imagine if hospitality page is predicting the demand for this year, and they have machine learning model, surely they would have to retrain the model with this year data, as the data would be very different to the previous years. In next stage, you have ETL, so extract, transform, and load. At this stage, you want to format your data, making sure it is in format your machine learning pipeline is expecting it to. So this can be done by a service, cloud service, or script. You can maintain your metadata, which is then helpful if you want to query your data sets, and then storing, once the data is processed, storing it in some kind of output. And lastly is the ML component. In ML component, there are two basic components or subcomponents. First is feature engineering and extraction. So at this stage, you process your data and extract features for the machine learning model to train on, and the machine learning model itself, but is being trained and validated and improved in loop. So at this stage, you need to manage the code dependencies, making sure that all of the libraries that you're using have the version that you expect, and everyone who's collaborating on the codes is using the same dependencies. If you want to run multiple machine learning pipelines in one place, you need to manage scalability. Each of them needs to be in a separated, self-contained environment with its own dependencies, as the versions of libraries being used may differ from one model to another. You need to manage compute resources. So making sure that the compute resource is available when you expect it to, whether it's CPU or multiple CPUs or GPUs. Then you need to manage model versioning. So you might end up having multiple versions of the model as the model is being updated and retrained, alongside with the model artifacts. And if you have a team of data scientists collaborating on machine learning development, then you need to manage source control and the code collaboration. So this being machine learning development lifecycle. Now moving to production, you would create a machine learning production pipeline, which has the extract, transform, load step that can be done using Spark, Python, R, or SQL. I'm sure there are other ways to do it, but these are probably the most common ones. Then you have the feature extraction and feature engineering, monitoring for data drift. And if the data drift or model drift is detected, then you want to retrain your model, store it as a new version alongside with the model artifacts, and then perform the inference. And again, the three most commonly used runtimes are Spark, Python, and R. So when you move once you've done development and moving into production, again, you need to manage the environment and all of the code dependencies, all of the raw libraries that the code is using. Make sure that the compute power is available. If it is batch inference, you would spin it up once in a while, making sure that the compute instance it's needed is available, or if it's stream, you need to manage high availability of the compute instance and scalability if needed. Then you, as I mentioned, retrain the model. If data drift is detected, you probably want to update the model, improve your machine learning pipeline, so continuous development and integration, and register logs or any error messages, progress of the code. So register logs in some form. So hopefully you're not overwhelmed by this stage, but these are all of the operations and management that's involved in machine learning development and moving into production. And there are three basic types of hosting machine learning model. One is on-premise, then hybrid, and in cloud. So on-premise involves the most management of the resources, managing the hardware, scalability, compatibility, any updates, patches, all of that. So in my experience, mostly I've seen this being used for small ML projects or just proof of concept, see whether the client wants to move forward with AI, or it's been used for clients who have very, very sensitive data, and at no circumstances the data can leave premises, and all computation and process needs to happen on premise. Those cases are very rare. Or if a client has legacy systems and they are not ready to move into cloud. Then with hybrid deployments, meaning part of it is on-premise and part of it is in cloud. Usually the data is on-premise and computation is happening in cloud. You have less to manage when it comes to managing computational resources and scalability, but still the data is on-premise and that needs to be managed, and the connection between on-premise and cloud needs to be managed, which is usually using virtual private cloud. And it's typically, or I've seen it being used when the data is sensitive and client wants to ensure high data security. And the third one being in cloud, where you potentially have least things to manage, as a lot of the heavy lifting is done by the cloud provider, especially when it comes to serverless applications. And all you need to do is make the services talk to each other, basically. So in cloud, meaning that both data and computation and development is happening in cloud. It is easier to scale it and manage access to it. So first, the on-premise deployment. This would be like most common, a typical example of on-premise deployment, where your machine learning pipeline is in self-contained environment, which can be managed by a Docker container, and orchestration being done by Docker Swarm or Kubernetes. And then you can do your model versioning and artifacts using MLflow, which is open source service for model registration and versioning, and source control being done using Git or Bitbucket. Or if you want to go having fully managed service, you can use HopsWorks. So HopsWorks is open source platform for machine learning development and operations. It allows collaboration between teams with managed access using single sign-on. It's using Airflow to manage machine learning pipeline. It has the Python, PySpark, Scala, and Flink capability. And you can do everything in it that you expect your machine learning collaboration workspace to do, and on-premise. So speaking from experience, this is one of the projects. It's actually the first project that I've done at Blackbook, which was on-premise. It is running in production, where the input was from local input folder. It contained a bunch of Excel files those were processed by UiPath, which served as an orchestration and ETL. And UiPath was calling the inference pipeline, which was a Python package installed at client side. It consisted of feature engineering, short-term forecast, long-term forecast, and formatting the outputs. The features were stored in pickle file as processed data temporarily that were then used for short-term and long-term forecasts. And the final output was stored in output database, as well as Excel outputs that was then sent again using UiPath to SME via email, alongside with any logs. So is this a typical on-premise deployment? It is not, but it made sense for the client to do it this way because they were already using UiPath for automation. It is something Blackbook is using, so we will use that for orchestration and ETL. Moving on to hybrid ML deployment, where data is on-premise and computation is happening in cloud, where high data security needs to be assured. Typically, virtual private cloud is used to access the computational instances through Internet Gateway. And there are many security layers that needs to be passed to manage the access, making sure that the right people have the right access following the minimal access policy. Then one thing to keep in mind with, this is example for AWS, and the image is from a Cloud Guru study material for machine learning specialty. So one thing to keep in mind with SageMaker and SageMaker Notebook instances is that by default, it accesses the public internet for SageMaker API and to access S3 buckets. So for to further enhance the security and keeping all of the communication within the cloud, this needs to be disabled, and the communication can happen through private link and S3 VPC gateway. And so from experience, the project that I was involved in, that is actually finished recently, was again forecasting task where the client app was producing CSV outputs on weekly basis. This was then loaded to Azure using Gateway into a blob storage, and the blob storage was mounted into Databricks. And inference pipeline all happened, was done in Databricks, first performing ETL, where the output was stored in Delta Lake, then fed into feature engineering script, and finally into forecast. The whole process was recorded, the logs were recorded in Delta Lake, in Databricks data file system, which is eventually a blob storage, and as well as pre-trained model that was loaded for to perform inference. So it was a batch inference, and Databricks served as for orchestration, and job was scheduled to run weekly. The final output was then stored in database. And lastly, in clouds implementation. So this is block diagram or example for Azure in clouds deployment. Azure has Azure ML as a workspace, a machine learning workspace service, where you can use notebook instances to create your machine learning pipeline, or they even have more user-friendly console where you can just drag and drop steps that you want your machine learning to execute. But in this case, let's say it's a bunch of scripts that are running. Once you train your machine learning model, you store it in Azure Container Registry alongside with all of the model dependencies and artifacts. You can also do model versioning, and then you host your service. You can host your service using Azure Kubernetes. Azure Kubernetes are usually used when the service needs to be constantly available or for real-time inference. So when you need to assure the high availability of your inference pipeline, you use Azure Kubernetes service, but there are other deployment options or hosting options as well that are less costly. And the model performance is recorded in Machine Learning Workspace. For AWS, it is the architecture, overarching architecture is similar to AWS as well. But one thing that I don't think Azure is doing is that you can deploy multiple versions of your model. So within one container registry, you can have let's say two or more versions of your machine learning model, and you can manage your traffic to each of them. So this is very helpful if you have new version of the model and you're not sure how it's going to behave in production. So you can load balance or direct 90% of the traffic to the old model that you know it's performing okay, and the rest of the traffic to the newer version of the model. And so the model performance is recorded in AWS CloudWatch, and the endpoint logs are recorded in AWS CloudTrail.
Can I just ask a quick question while
Sure.
we're there? If you want to go back to that previous slide, you're saying that model split, right? So one of the things that I have done in the past is that we build this thing so-called the model manager. Now, what the model manager does is just simply as a way to very much just to distribute the amount of the input data or amount of the cases to each of those models, right? So my question though is not on that, but my question is, one thing that I pick up is, apart from this slide, you have multiple models, but do you often have what I call a champion model? So a champion model is where the one that you know is performing well. Then as you have more model coming in, you gotta have a benchmark, and champion model itself is a way, a good way to benchmark to say, with whatever new model that you're training in, how are they performing? So that's first question. And to some extent, your champion model can be even what I call do nothing model, because sometimes do nothing is perhaps the best thing to do. Do you do this sort of thing at all?
So, yes, absolutely. So during the machine learning development, you would try multiple models, not only different settings of one model, but also different algorithms altogether. And then you establish which one is your champion model. So you start with some baseline. So, you know, if it's if you toss a coin and let's say you do classification and you have two classes, then equally you have 50% chance for it to be one class or another. So that's your baseline for classification. And then you have a bunch of models that you trained, and you come up with your champion model, which is the best performing model. Depends on what metric you use, whether it's precision, recall, or area under the curve, or F1. And let's say you decide to deploy that model in production. And then as the time goes, you might need to retrain that model because the data changes, or you come up even with a better model than that one. Then you can use this scenario to deploy second model in production and direct partially the traffic into it, rather than swapping it all together, to be safe that this model is performing as expected in production. Did that answer your question?
I think so, yeah. So, one way that you direct the traffic to different model, and obviously within each of the model, you have your various lever. What I call lever is like, or sometimes I call it switches. So within each of the model, you have multiple switch. My question then is, do you then have an overall arching model that look at the entire portfolio? So what it does is that once within the model, it does its work in terms of whatever things that it does, but it also takes of the entire portfolio to say, I want to achieve 4% of the retention rate with 2% in terms of the profit margin, and hence it gets further restricted. So it's like the second level of the lever that you are maneuvering. Do you try to do that?
Right. So it's saying you have like multiple aspects or criteria, success criteria for the model.
Yeah.
Yeah, so we usually create like a dashboard for the client where these metrics are being tracked, and there we monitor each aspects that are important for the clients, how the model is performing.
Great, wonderful. Thank you.
You're very welcome. So the in-cloud project that I've done and I'm about to finish is using AWS services. So the data source, I think it's on premise, and they're using Glue to process this data and store metadata. They store it in data lake, which is nothing else than S3 bucket, and then use Athena to query this data lake. And for me as a data scientist, I access machine learning workspace using AWS DaaS, which is desktop as a service. The access is managed by AWS Cognito. And within the workspace, they use Kubeflow to spin up a Jupyter instances. So Kubeflow is like simplified Kubernetes. It has all of the power of Kubernetes, but it's very simple and easy to spin up an instance and just set up number of CPUs, memory, and CPU or GPU and memory. Some final thoughts. There is no size that fits all. It always depends on client, what's their target, what they're trying to achieve, whether they want implementation machine learning solution that is fastest or requires the least maintenance, in which case you would go with cloud serverless services, whether they want to perform batch inference or they want to stream the data, you would use different services for that. Whether the computation requires CPUs, multiple CPUs or GPU, usually for images and video, media processing, GPU is required, and who's going to maintain it. So those are important questions to answer when considering the production deployment. And it's always good to, or most of the time when it makes sense, it's good to leverage existing infrastructure. So if clients or your organization is already using Azure or AWS and has something running there, it makes sense to go with this cloud provider. That about wraps it up. Any questions?
I asked my question already. Any question from everyone else?
Hey,
Adam here. Can you hear me?
Yes, we can hear you. Go, Adam.
Hi there. Hey, thank you, Alexandra. That was really good. I guess I have a question a little bit more generally around, as a senior data scientist, are you actually building those cloud infrastructure components? Are you there in the nitty-gritty, or is there a different type of role that is typically doing that actual DevOps and pipeline activity?
In some cases, yes. In others, no. So, for example, in this case, this in cloud architecture, it's been already set up, and I just came in as an external data scientist and used the machine learning workspace. But in other cases, we do, or we at least advise what architecture would be suitable. So in this case, we had nothing to do with the on-premise, how this is being ingested, but we've designed everything from connecting the blob storage to outputs. So the inside of the clouds we've designed, but how data is being ingested, we haven't. But we provided guidelines on how to do that.
Right. Okay. Thank you.
Would you be hands-on in doing those things, or it would have to be done? It would be done by someone else in your team.
Pardon, say again. You were breaking up a little bit.
Would you be involved in building up some of those things, or it would be done by someone else in your team?
Yes, yes, it's me. Yeah, I was designing it or advising on it.
Hey, Alexandra, thanks. Really, really good presentation. Thanks for that. I just have one quick question just to hear from you. What are your thoughts about feature store? Have you ever come across feature stores? Have you ever designed one?
So yeah, HopsWorks is a feature store.
Yeah.
We've
Sorry, for people who, like me, who are not familiar what is feature store, trying to quickly go through what exactly is feature store.
Okay, so how do you treat data engineering, where you actually do some transformations on your data for your you can filter your data, or do some business logic, pure ETL, right? So that is called data engineering. So the same thing when it's done for machine learning, there's a step called feature engineering, right? So imagine an organization where there are multiple models are getting built, right? And they want to have a central place where they actually create all these features, pre-computed features with all the feature engineering. So that the place where they store these features called feature store. And then the feature store is then used to actually build the models. Either, it's used for training and is used also for inference, like a batch inference or a real-time inference. So there are a couple of products, open source ones. There are HopsWorks does that. There are a couple of other products as well. I think Lyft has also implemented one feature store. So yeah, I just want to understand your take on that, Alexandra.
it was actually only one project that we it was tender for. Well, anyways, I can't say for who it was, but
Okay.
it was tender that we applied to, and we suggested to use HopsWorks. And that was actually the only client that we've seen directly requesting having feature store. Other clients, not so much.
Right. Okay. Cool. So I've actually implemented this the end-to-end machine learning pipeline using MLflow and all the other components of Databricks, right? So how do you usually go about debiasing your model in real time, right? Based on drift, there are two types of drift. It could be a data drift, it could be a concept drift, right? So how do you detect,
How to detect data drift?
data drift or concept drift? How do you differentiate between data drift and concept drift?
What do you mean by concept drift?
Okay, so data drift could be because you did not have your good sample when you trained, right? And the ones that you're getting in real world after your model is deployed deviates from what the training set actually was, right?
Yeah.
So it was not a representative training set. So that could cause your model performance to degrade, right?
Yep.
So data drift. Whereas concept drift is, imagine you would have thought when we were building the model as an SME that, okay, these are the features that I need to take into account. And this is the business logic. For example, let's take spam detection, right? So you would say that when you built a model, you would have built telling that, okay, if you get from this kind of regex pattern email ID with this kind of subject, it's actually a spam. So your model would have trained based on that. But over time, the concept of spam detection itself is changing. So you might have to bring in new features, right?
Right.
Change
Okay.
logic.
I haven't experienced the concept drift,
Mhm.
but have accounted for data drift.
Okay.
So would measure whether the new piece of data is statistically different to the trained data, and that's where the data versioning comes in handy. So I know what was the version of data the model was trained on, and whether it's different to the current data, and then triggering automatic retraining before the inference is done. So that was used for the hybrid model that I worked on in Databricks. And every week, the model would check for data drift before performing forecast.
Perfect. Okay, so you kind of have a metric dashboard or something where you're looking at a specific metric of that particular model, and then have a threshold. So you're seeing if it dips.
Yes. So,
okay.
yes, exactly.
Perfect. Cool. Are there any other questions, folks? For those who have joined late, this is recorded, so it'll be available in YouTube as well. Yeah, but feel free to ask questions, Alexandra.
I have another question if no one else is.
Sure, go ahead, Adam.
I guess, do you have to worry about deploying multiple environments? Are your MLOps processes here geared up to support multiple environments? I guess with your model, are you perhaps taking the same model and deploying that into each environment, or is it potentially do you have like a development environment, a test environment, a production environment, and instances of those models, whether they're potentially the same version or different versions that are going through various QA processes? Have you had to deal with that at all?
Okay, so you don't mean when there are multiple machine learning solutions running in one platform, but the small like spacing out or differentiating between development, test, and production environments. Is that correct? Yeah,
it's definitely the differentiation between those environments. More from the software engineering perspective, how you take the software through the development, test, and production lifecycle, and you have QA processes built in there. Can you talk maybe a little bit about the difference with MLOps in that regard?
Yep. So if it's on-premise, you can use Docker containers to manage your environment. And within Docker container, you have the requirement text file, which installs all of the libraries and all of the dependencies. And if this is in cloud, once you trained the model in cloud, then you can register it in a model registry, whether it's Azure or AWS. They both have the concept is similar. It registers the model, including all of the dependencies that the model was trained on, all of the libraries. So then for inference, it's calling that container registry and performing inference from there.
Mm-hmm. How many versions of the model may you be, or are you typically training at once? Is it just the one because you've only got the current, say, week's CSV file from that particular client application that you're talking about?
How many versions of the model?
Or are you having multiple experiments, training different variations and potentially different architectures of the model? And is that built into this process that we're seeing here?
So this is like production pipeline or production, how the model is running in production, but during development. So development was also done in Databricks, and there would be like multiple Jupyter notebooks having different models being trained in it with different settings, and right. They would be done in parallel. Yeah, so there would be the development environment, and then once we have the champion model, right. Then we would register that one with dependencies and store it in pickle file or binary file.
Yep. Okay, great. Thank you.
You're welcome.
If there is any other question, I think we will call it the end. And again, thank you so much, Alex, for presenting this. I absolutely have learned a lot, especially some of those examples that you have given. I really appreciate your time. And thank you so much again.
You are welcome, and thank you for having me.
Thanks, Alex. Really appreciate it.
Thank you, Alexandra.
Thanks,
thank
everyone.
You. Have a good evening.
Good evening. See ya.
Bye.
Bye, Alex.
Bye.
Bye. See you, Jason.
See ya. Bye.
So, bye.